Okay, so first, I want to show some examples. So the example of how can we can use queue, some practical example of queue, some implementation of queue, practical implementation. So
Of queues.
yeah, of queues.
Of queues.
Yeah, of
Some
queues.
practical of queues. Yeah.
Yeah.
Okay.
So of
Okay.
queues.
Okay.
So that is the breadth first search traversal on a graph. So
Okay.
um, here we mean by graph
Oh, are you
the
recording? Are you are you recording, Vadim?
now first let's let's remember what a breadth first search. First, so our objective here to start at some node and traverse through the entire graph by first visiting all the neighbors of the starting node, then visiting on the neighbors of the first node we have visited, and so on. So we can think of each iteration of the BFS as expanding the frontier by one node outwards at each step. So that is where the queues will be helpful, but we're going to talk about it a bit further. Okay, so uh, uh, so now let's start, for example, at node 0, and we'll try to do a breadth first search from this point. Okay, so first we
Okay.
begin at 0 and add 0 to the frontier, or the visiting group. And next, we visit
What?
all the
Visiting
neighbors.
what? Okay.
Sorry. Okay, so
Go ahead.
then we are visiting all the neighbors of 0. Those are 1 and 9, and adding those to the frontier. So if you can see it from the slide, is the slide is clear enough? Okay. Okay. So we're adding those to frontier. That is highlighted in orange or in yellow. So now we visit all the unvisited neighbors of 1 and 9, being only 8. Okay. So similarly, we are visiting all the unvisited nodes. So here, the only unvisited node is of 8 is only 7. But 7 has a lot of nodes now. We need to visit every node of 7 and add them to frontier. So as we're now an important note is that we are now looking at the neighbors of 7 at the frontier of the visiting queue now here, and once we're starting to look at 7's neighbor, we have to mark 7 as visited, and so we're visiting every neighbor of 7, and we visit all the unvisited nodes adjacent to those that were neighbors of 7. So adjacent to the nodes in our frontier, in other words. Okay, now we have visited all the
Okay.
nodes that all the nodes in that no of the of this tree, not tree but graph. In this graph, we have visited every node here, and we'll leave 12. We visit all the nodes except 12 because we can't reach it we can reach it from the node 0 at which we have started. So we're leaving it as a loner node, and so that is what we want to do. So now that we know what a BFS is, we can look how to implement it. Well, this is where the queues becoming useful. So the idea here is to add the starting node to the queue, and visit all the unvisited neighbors of that node adding them to the queue. So at some point, our queue would become empty, and that means that every element had visited, and BFS will determinate, and that's what we want. So let's walk through the pseudocode. So first we're declaring the queue variable, and that would be the queue. And we're going to enqueue to our queue some starting node that we started with. So the last slide that was node 0. So now we are marking it as visited. So the starting node dot visited is equal to true. So and now we are starting our while loop, and that is why we want to make it while queue is not empty, because once it's empty, we run out of nodes, and that means the BFS will terminate. It will terminate, which we want here. So now we want to save the node that we're dequeuing to node variable, and next we want to loop every neighbor of node, and we're using neighbors method for this. So we're looping for every neighbor of neighbor's node, of neighbors of this node. So if this neighbor that we are now currently processing has not been visited, or in other words, if the neighbor dot visited is equal to false, we're changing this value to the true, and we are enqueuing it to our queue. So this queue represents the frontier, and that is why we have to maintain this queue, because that would be the frontier in our case. So now let's move further. One moment. So now let's look at some implementation details of queues. So how can we create and process with this data structure? So now it turns out that we can implement queues in multiple ways, but the most popular are 3 ways: using either arrays, single linked list, and double linked list. So now let's look how to work with how to implement there with single linked list, but in the source code implementation that I also show today, we'll look the double linked list version. So now let's look how we can implement the enqueuing and dequeuing operations, the most important operations in queues. So first of all, we have the tail pointer and the head pointer. So here they're both pointing to the null value. So next, for example, we want to enqueue
What is
5.
Why do they point to the null? Why do they point?
Because
before you add anything.
So at this point,
there was nothing there.
There was nothing. So the queue was empty. So now we add 5, and here it's not so interesting because we're just adding, and the tail and the head pointer remains at 5, the element we have just added firstly. But now, next, we want to enqueue another element, and that is where it becomes interesting. So here we we are enqueuing 1 and moving the tail pointer to the element we have just added. In this case, to the 1.
Okay.
So next, for example, we want to enqueue 6. The head pointer will remain at 5 at our first element, and the tail would now be at 6. So we want to change the pointer position to 6. And next, we want to enqueue 17, the same thing, the same way, and now 8. So now that is how we can enqueue. So in other words, to put it differently, we have to add elements to the queue, and we can say here okay, so and set the tail pointer to the element we have just added. Okay, and now let's look how we can dequeue some elements from the queue. So initially, we want to dequeue the first element.
Okay. Before you go too far, okay, so I notice you use the word "some" too often. Some. Okay, so you just don't use that word. Okay, so because it's okay, so repeat what you just said, but don't use the word "some."
Sorry?
Повтори предложение без "some."
Okay. So what if the sentence was?
Oh yeah, that just said. Okay, you said let's look at some. Okay. No, продолжай.
Okay. Thank you for.
Can't remember the sentence, but it was, but it used the word "some," and I said, what does that mean? Okay, so anyway, continue.
Okay, thank you. Okay,
Yeah,
now
okay.
let's look at how we can implement the dequeue operation in queues. So firstly, we want to dequeue the last pointer, or the first pointer, the element we have added first of all. So that in the queues we want to pop that element from the end, from the beginning, we can say this. So to do that, we need to move the head pointer ahead a node, and setting the last node to null. So here, this null, nothing points to this element, and it is equal to null. So this means that it will be picked up by the garbage collector. So if we're coding in Java, for example, or in other languages, but if we're using programming language such as C++ or C, that requires to deallocate memory by ourselves and free memory yourself, at this point we have to free the memory and deallocate it to get to avoid memory leaks. Okay. Now next we want to dequeue another element, 6 for example, and we perform a similar operation. The same thing for the rest of the queue, to do a dequeue operation. And all we need to do is move the head pointer one step and set the current head value to null, and it will be collected by the garbage collector. Okay, and when we have no more elements, both pointers should point to null again, as in the beginning, as it was initially. So as we have observed from enqueuing and dequeuing operation, that is all moving the pointer, the head pointer or tail pointer forwards. So in the case of enqueuing, we're moving tail pointer forwards, and in the case of dequeuing, we're moving the head pointer forwards for dequeuing. Okay, and now I want to, one moment, I'll turn the demonstration off for 1 second.
Okay.
Okay, so now let's look at the source code for Q's data structure. So first, initially, we want to create a linked list, and we're going to use this linked list for to implement our Q. So here we have two constructors. First is when the user creates or a user. I think a user wants to create an empty queue, and another one if the user wants to create a queue with some element, with the element. Yeah, and so we are going to use offer function here, offer method. So this offer method just means to enqueue, and that would be a bit further. And now let's look really quick at some methods for queues. So the first method is size. So this would return the size of our queue that we have now maintaining, just the size of it. And for this method, we are using built-in function for size of linked list we are using to implement this queue. So the size method is just built-in function with linked lists. And next, the next thing we want to write here, what does this equal sign mean? With the next thing we want to code here is empty function, is empty method. So if the size is equal to 0, we're returning true, boolean value equal to true. Otherwise, we are returning false. So is our queue is empty? We're returning true. Is the size is equal to 0? And now let's look at peak as the peak method. So what this method does is that peaks the element at the front of the queue. So this, without removing it, without dequeuing it. So the method, we want to throw an exception if the queue is empty. So is empty, we're using here the method we have just wrote, we have just looked at, is empty. So if the queue is empty, we're throwing exception, new runtime exception, queue empty. And otherwise, we're just returning peak first function. So that is the building function again with our double linked list that we're using to implement this queue. And next, we want to take a look at the pull method. So this would pull the element from the front of the queue. So that is the same thing, pulling, as dequeuing. So we just call it another way. So that is pulling, dequeuing, the same thing. And so where is the queue is empty, we're throwing the same exception as here. So that thing is the same. And otherwise, we're returning the building function again. Remove first, so that removes the first element from the linked list or the queue that we're now maintaining. And next, we want to add element to the back of the queue or in-queue the element, and we want to use offer operation here, often method here. We want to write it. We're just adding last, so this time we don't need to write some exceptions. The checks for exceptions, because we can add the element to the queue anytime. And next, we want to write iterator. So iterator allows the user to iterate, to traverse through the elements in the queue. So using, for example, a for loop, we can iterate through the elements inside the queue. So we are using this override to change some settings of the settings, we can say it, of the data type, and we're using here iterator that is also the built-in function. So that's the end of the code. So it is built. This data structure is built a bit easier than others, because here we are using the built-in functions with double linked lists. So double linked lists are used here to operate with the queue and to create it. So that's it for my talk with queues. Next time I'm going to
Great.
take another data structure or algorithm. Thank you.